So, welcome back. I am Zafer Gedik from Sabancı University. Actually, I think I am the one who knew Durmuş for the longest time. It was 40 years ago. I was in Metü and taking a course, by the way, from Tosun Terzioğlu, linear algebra. It was exactly 40 years ago. Durmuş is a bit younger than me. Actually, his official age and the real one are a bit different, so he is even younger. But I knew him from his first days in Middle East Technical University. So this is more than 30, almost 40. Well, this second session starts with a speaker from a host institution, again, Alhun, Aydın. Alhun Hoca will talk about things, some related to condensed matter physics and some new quantum systems. But this has close connection with well-known effects in quantum field theory. I knew about Casimir force, but I'm curious about torque. So,
hi everyone. My name is Alhun Aydın. I'm from Sabancı University. So as Zafer Hoca mentioned, this talk will be a little bit different from the previous talks, probably also different from the rest of the talks. I am not working in high energy physics. I'm working in the intersection of statistical physics, quantum physics, and condensed matter. And here in this talk, I wanted to have at least some connection with the high energy physics. So I looked at my past, what I have studied, and actually an effect that we have proposed, quantum shape effect, is somehow related to the Casimir effect. So I picked this topic. Okay, so first let's talk about briefly about the Casimir effect. Let's imagine two parallel plates like this. It can be metallic, it's better, but it doesn't have to be. So these are two surfaces, and this is placed in the vacuum. All right, so there's nothing else. So if you make these two plates close enough, you will realize that they will attract each other. Well, this is surprising because there is no force acting on the system. So it's in bare, in vacuum, right? So that's why this is a very interesting effect. The reason this is occurring is because of the fluctuations of the electromagnetic field. So as you see, this parallel plate creates some cavity here, which is different from the rest of the system, which extends to infinity. So this difference, you can see this difference in the vacuum energy density. But here is a very interesting thing. If you calculate the vacuum energy, well, these are the electromagnetic modes, and these are summing from 1 to infinity, right? So basically you are summing infinitely many terms, and this sum is divergent. So, this sum is divergent inversely, like inside the cavity and outside it as well. So what do we do? Well, actually, we are not interested in the absolute energy density here. And we are looking at the differences of the energy densities, right? So we are looking at the difference between the cavity energy density here and the energy density outside of this cavity. So when you take that difference and when you apply some mathematical techniques called regularization, which is basically multiplying the summation with some well-behaved decaying function, you reach this finite result. So you basically take the difference of infinities, and infinities cancel with each other, and you get some finite term in the end. And this is the Casimir force in 3D. Okay, so now let's talk about some other effect. This quantum shape effect is actually an umbrella name for the physical effects that are arising when you do size invariant transformations to your system. This system is a quantum confined system. And so this effect is predicted first by us in the summer of 2015 in the office of my then PhD advisor. We were discussing some other problem, and somehow the discussion extended into something else. And then this is kind of like the timeline of this effect. Well, after 2020, of course, there are many studies I have done, but just for the record. So I will talk about what size invariance and all that stuff mean, but why? First, I would like to say why we are motivated to find this kind of effect. First of all, quantum size effects are actually the theoretical backbone of the nanoscience and nanotechnology. So my then PhD advisor was working on quantum size effects, and he already had developed two methods, analytical methods to basically predict them. Well, but there was this ambiguity between, like, people say, okay, size effect, shape effect, but what do we mean by size and shape? That was really not clear in the literature. So we wanted to basically distinguish size effects and shape effects from each other. And secondly, we asked this question: is it possible to change the shape of a domain without altering the sizes? So briefly think about this. This is kind of tricky question. I mean, it's not it's a very simple geometric question actually, but it's not as simple as you think unless you see the answer. Okay, so of course, when we say size, shape, we need to be more concrete here. What do we mean by size? Well, size is defined in math very rigorously under the Lebesgue measure. Here, let's take a cube, for example. We have the bulk size parameter, which is the volume of this cube. But there are also lower dimensional size parameters. So we have two-dimensional size parameter, which is the surface areas of this cube. There's 6 of them. And peripheral lengths, these side lengths, and the number of vertices here, the corners of this cube. So these are called geometric size variables. So when we say size effects, we are actually modifying one of these variables here, okay, in our system. Okay, so this is well known. So we have quantum confined systems. Well, the properties of your materials can be size dependent when you reduce the sizes to the nanoscale. And well, this is due to when you reduce the sizes to the nanoscale, you are basically reducing it to the order of thermal de Broglie wavelengths of particles, which is basically some quantity that is describing the average or thermal wavelength that you can assign to these particles. So that's basically generates the importance of the discrete spectrum. We always have this discrete spectrum, but quantum mechanics works at any scale, but the importance of the discrete spectrum actually becomes more prominent when you reduce the sizes. Okay, so this is last year's chemistry prize has given to the quantum dots, which is basically this topic's application. Well, it turns out that you can write any equilibrium property in this form. So let's say, for example, this can be free energy, a thermodynamic quantity. This is the classical term that when you see, when you open your statistical mechanics textbooks, you will see this term. But there are also, which is volume dependent, but there are also additional terms which are called quantum size effect terms directly related to these lower dimensional size variables. Okay, so this is also in connection to the previous talk. This makes the thermodynamics non-extensive at nanoscale because these terms are here. Okay, so another question here is, Are these all the effects that we can consider? Is there anything else that we can add here? I mean, we don't add, but emerge from the system. Well, let's turn back to the quantum shape effect. So how we, when I say size invariance, I basically mean the keeping all the size parameters constant that we have discussed, but still be able to change the shape of a domain. So how can we do that? So we come up with a very simple method. So let's look, for example, the 2D version of size invariant shape transformation here. Okay, so my domain is like this. So in this blue region, the electrons are. And if we let this inner square to rotate with a fixed, by fixing it at the center, we can reach this another configuration. So consider this as the initial configuration, and this is the final configuration. And let's compare these two. Under this operation, we haven't added or removed anything from the domain. So the area of the domain stays constant. Well, let's look at the peripheries. Well, that's as well. The number of vertices, there are 8 of them. Here, there's 8 of them as well. So all the size parameters stay constant under this rotation of the inner square. But as you can tell from your intuition, shape of the domain is changed. Well, not only you realize this, but also electrons living in this, confined in this domain also realize it. Think of yourself as a particle or a quantum wave. You are traveling here. It is quite different landscape when you travel along this elongated tube when compared to this triangle like regions, right? So, okay, how do we see the effect of this on the physical properties? Well, as you can imagine, this enters to the Hamiltonian as a potential term. So basically your boundary conditions are here, and this is, for example, like a free electron Hamiltonian, and you are basically solving time-independent Schrödinger equation to find the energy levels for the electron that is confined in these shapes, different shapes. So this is size invariant shape transformation. So this is, although this looks like a simple effect, it's actually, it has very profound consequences. So let's look at one of them. So let's calculate the quantum shape effects in thermodynamic properties. Since we are familiar with this shape, I'm not explaining it again. So we have this shape, we're rotating it, the inner square, and we have this system is in contact with a heat bath, which means we keep the temperature constant. All right, if you look at already, I mean, these are not for illustration, these are real spectrum. So the energy eigenvalues scale quite differently under this operation. This is unlike a size effect. In size effect, energy levels scale with 1 over L squared, right? So when you increase or decrease the size of your domain, all levels will scale uniformly. But here we have something quite different. As you see, under this operation, each level is affected differently from this operation. Well, okay. Now, by the way, I'm making these changes quasi-statically. So we are looking at the infinite time limit of this operation, but finite time operations are also possible. Similar effects are there as well. We are studying it. Okay, so here are the thermodynamic quantities, for example, free energy, entropy, and internal energy that we have calculated. Well, that's weird. Symbols are not there, but let me explain. So this first one is the partition function changing with theta, the rotation angle. So at 0 degree angle, we start from this configuration, 45 degree angle. So this is some in between angle. In the 45 degree configuration, you get this diamond shape, all right? So this is free energy. And what free energy tells you? Well, free energy tells you the direction of the thermodynamic transitions. Okay? So basically, if it's decreasing, it means that if you let the system behave, it will transition to lower its free energy. So okay, this means that if we let the system fixed in this 0-degree configuration, it will slowly transform to the 45-degree configuration. So it will rotate. This is entropy, and this is internal energy. Have you noticed something weird here? Normally, in the thermodynamics of gases, we expect free energy and entropy to behave oppositely, right? When you let a gas expand, for example, the free energy will decrease and the entropy will increase. But here, we have something quite different, which is not seen in the classical thermodynamics of gases. The entropy decreases. So, in other words, what this system tells us, the system tries to reduce its entropy spontaneously, because this free energy tells us the direction of the spontaneous transition. So this is quite interesting. Immediately, you might have asked, like, is this violating second law? Of course not. That's not possible. Why is that? Is we are making everything, all these changes isothermally. So system basically exchange energy with the heat bath at all times, okay? But it is still surprising that even under these conditions, the system tries to reduce its entropy. Okay, so we have, as you see, this is very non-trivial behavior from a very trivial looking transformation. So for the next discussion, I would like to mention a concept called quantum boundary layer. This is also important. So let's think of the room, of the gas in this room, for example. It's homogeneous, right? More or less. Well, we might have wind because of the air conditioners, but more or less it's homogeneous. And that's what we expect. But when you reduce the sizes to nanoscale, the electrons, the density distribution of the electrons become non-uniform, like this. So this is, as we said, right? So this is an electron gas confined in this kind of shape. And if the length is 2 micrometers, you see more or less, so this is the red regions are the high probability, where the electron has higher probability. And near the boundaries, since the boundaries are Dirichlet, the wave function has to go to 0 there. We have a blue layer, which tells us that electrons cannot be very close to the boundaries. Well, okay, but it is more or less uniform. When you reduce the sizes, you see that there is a layer, there's a blue layer developing near to the boundaries. And this is a thermal distribution, by the way. So this is not a distribution of one electron. It's thermal statistical distribution of all the electrons in the system. And it is calculated by this function. It's called quantum thermal density. You have the psi squared quantum probabilities of the electrons weighted by the thermal probability, which here you enter the eigenstates because the system is relaxed. Well, okay, so this is a quantum effect because this is related to the thermal de Broglie wavelength of the particles. And if h bar goes to 0, you basically don't have any quantum boundary layer. Well, okay, this was important for the next discussion. Now, I promised you some forces and torques related to this effect, right? Well, remember, I have told you this inner object, if you under no friction, it will spontaneously rotate. That I promised you. Well, in order for rotation to occur in this kind of shape, there has to be non-uniform pressure distribution along the boundaries, right? Let's say we have some boundary here. If electrons exert the same pressure at each and every point, we don't have torque, we don't have difference in the pressure distribution. But when we look at it, you already might intuitively see that, well, it looks like electrons are more concentrated in this part of this region, and they could exert more force on this part of these walls. That's what your intuition tells you. Let's calculate it. So you can basically calculate how you can calculate the pressure, for example. Well, you can make small perturbations along the boundaries and look at the system's response to these perturbations. So when you do that, you get this figure. So this is the normalized pressure, normalized to its maximum. And this zero here is actually the center of this wall. So basically we are looking at the pressure distribution along this wall. And as you can see, there is a strong tendency to the right of this graph. So basically the moment arm is here. So it's shifted from the center. And this tells you that, well, there is a non-uniform distribution and this thing should rotate. Well, the good thing is that this effect is fourfold multiplied because we have similar situation here, here, and here, all tries to rotate this object. Okay, so we can calculate torque basically from the difference of the rotation, sensitivity to the rotation angle of the free energy. And we also have, like you see here, exact and overlapped quantum boundary layer results, which is our analytical method to predict the exact behavior. I didn't explain it to you. We don't have time, but we also can analytically predict these behaviors. So this is how torque behaves, as it should. It starts from 0, it increases, and it decays to 0 again. Well, you can immediately see it from here. At 0, we don't have variation in the pressure distribution. You see this wall is exerted the same pressure from everywhere. Here as well. But in between, there is a pressure distribution. So if you give a little perturbation here to this domain, make it 1 degree or so, it will spontaneously rotate to the 45-degree configuration, as this finite torque tells you. And okay, connecting to the Casimir effect, you can think of this as a matter wave analog of Casimir effect. So instead of an electromagnetic field that is making the job here, we have electron gas actually doing this. Okay, so lastly, I would like to mention a direct comparison with the Casimir force to see where we are. Of course, this is as direct as possible because we have different conditions from the Casimir effect. So in the Casimir effect, we have this two reflective surfaces with a distance A, and this is 2D Casimir force. So I try to mimic this in the aspect where in the quantum confined systems we can work. So we have the same wall here. So this is basically, I mean, you don't see the density of the electrons here because I was lazy, but this is basically the discretization of the domain. Well, so the electrons are here, okay? And within this region as well. So basically, we have the same opening here, and we are looking at how, so this inner square will try to stick to this boundary, right? And if we calculate it for this specific system, where I take the gallium arsenide conduction electrons, well, because the electron effective mass was very small, and even at high room temperatures, we get this kind of a curve. So here, the blue one is the Casimir force, and the orange one is the quantum force, or force due to quantum shape effect here. Well, this is a kind of a cherry picked, of course. I mean, you can modify this graph as you please by changing this N and temperature, also the material. But here you can see that at very low, very short distances, Casimir force dominates heavily, but at intermediate distances, you can see that the quantum force is actually more dominant, and then they all decay when you increase the length. Well, in the past, we have done several applications of this effect. One was designing new type of quantum heat engines based on this effect. Well, this is quite interesting because you can define new cycles that are not present in the classical thermodynamics. We have new process, for example, here. We call it isoformal process, which means you in addition to the isochoric process, you have the shape of the domain preserved. And one catchy result from here is you get the work output from the cold side of the cycle, unlike in the classical thermodynamics where you get from the hot side of the cycle. So this is, and there are more interesting things here, but I won't go into. The second thing I want to mention is you can design new thermoelectric devices based on this effect. Remember, in thermoelectrics, we have a PN junction, right? Basically, because why? You want a different type of charge carriers to run the current. But here, you can have exactly the same type of charge carriers, but confined in different shapes. And you might think like, okay, this will actually result a very measurable kind of a large voltage difference on the order of millivolts. So this is indeed measurable, but haven't been measured yet. Okay, lastly, I want to mention some like future works. Well, this is, as I said, like this is a broad phenomenon. This can occur in any finite level system as long as you do some transformations in a size invariant manner. And although I showed everything here in position space, well, it doesn't have to be position space as well, right? It can be a reaction coordinate. It can be any variable as long as you keep the size invariance so that you can leverage the importance of the non-uniform level scaling, which I haven't mentioned a lot, but yeah, it's a long topic. Okay, so nowadays I'm working on the open quantum system extensions of this. And if you are interested more, these are some recent papers about this. And yes, so I'm glad to be speaking in this meaningful event. So I unfortunately had a very short time spent with Durmuş Hoca, but he affected me already within that short span of time. I really miss our discussions during lunch. So his work ethic, sincerity, and kindness was remarkable. Yeah, we miss him a lot. Thank you.
I'm curious to know. What's the frequency of when you are in this 45-degree position? What's the frequency of oscillations? That was the most, I mean, the lowest energy, right? Then when you're close to this 45-degree, there's a frequency. Is it sort of depending on the geometric?
Are you talking about the fluctuations?
Yes, yes.
Okay, yeah. Yeah, fluctuations depend on the number of particles that are confined in the domain. But in this study, we haven't considered, okay, of course, we used a lot of particles so that we can do statistics in the first place. And also we can get away from the fluctuations, at least the simple one over square root n fluctuations. But there are other type of fluctuations which will be important in finite time studies of this. But I would expect that like a wiggling motion at the 45-degree to be not very like important, just as an intuition, I can say. I didn't do the calculation.
In one of your last slides, you mentioned some millivolt potential difference, and you mentioned that it's not measured. What is the reason? It seems that measuring millivolts should not be a big problem. Has this been tested by experiment? Or?
Well, nobody has attempted. So yeah, I mean, it's I can imagine. So right now I'm talking with some professors from Sunum to realize this. We also thought like it should be easy to measure, but the problem here is from the experimental point of view to construct such a system. So what we are talking about here is very like a small distances, and your materials has to be perfect. And also when you try to measure things, you're basically inserting some contacts. So it becomes an open system, and there are all sorts of like difficulties arise from there. But I still think, I mean, we still think it's doable. Not like a very, but maybe there are not many motivations yet for that. But we are working on making those motivations.
Well, our next speaker in the session is Shahin Sheikh Jabari, getting a coherent arrow of time. Well,